Hi everyone, my name is Muhamad Akbar Osman bin Hashim. My presentation today focuses on how surface treatment effect influence dimension decision in high mix low volume precision machining and how this effect can be systematically integrated into early stage design and manufacturability decision through a structured decision support approach. Low volume precision machining requires highly consistent dimensional decisions across multiple manufacturing stages. It plays a critical role in high value industries such as semiconductor equipment, automotive components, medical devices, and precision machinery, where tolerances are often at the micrometer levels. In these environments, even small dimensional errors can lead to functional failure, assembly problem, and or even product rejection. Typically, components undergo multiple stage machining followed by surface treatments such as anodizing, plating, or coating, which introduce additional dimensional uncertainty. Combined with wide variation in material, geometries, and tight delivery timeline, engineers are required to make rapid and accurate decisions, making dimensional control in HMLV production particularly challenging. Most dimensional problems are not caused by machining accuracy itself, but by early engineering decisions made before surface treatment behavior is fully understood. Processes such as anodizing and coating introduce dimensional change through oxide formation and build-up, which directly affect functional fit and tolerance compliance. In high mix low volume environments, machining allowance and tolerance decisions are difficult to define and are often constrained by time, leading engineers to rely heavily on individual experience. Existing ISO GPA and SME standard focus on functional definition but provide limited guidance on early stage surface treatment effect, causing dimensional impact to be considered too late. As a result, there is a clear need for an integrated calculation-based approach to support early tolerance planning and reduce scrap, rework, and also quality-related costs. This study is guided by two main research objectives. The first objective is to analyze the impact of surface treatment processes on dimensional variation within high-mix, low-volume precision machining environments, with particular attention to treatment-induced build-up and dimensional changes. The second objective is to identify limitations in existing tolerancing and manufacturability approaches, and to develop a structured decision support perspective that integrates surface treatment-induced dimensional behavior into early-stage dimensional and tolerance planning. Together with the two objectives, this objective aims to support more consistent, data-driven engineering decision in the precision manufacturing. It's guided by two main research questions. The first question examines how surface treatment processes such as anodizing and coating influence dimensional variation and engineering decision-making in precision machine components, particularly in high-mix low-volume manufacturing environments. The second question focuses on how this surface treatment-induced dimensional change can be systematically incorporated into early-stage dimensional and tolerance planning in order to support more consistent and reliable engineering decisions. Together, these questions frame the motivation for developing a structured decision support approach for tolerance composition in precision machining. This slide summarizes the key findings from the preliminary literature review. First, dimensional variation in precision machining is influenced by multiple factors, including material properties, thermal behavior, machine setting, additional processes such as heat treatment and measurement precision. Second, surface treatments such as anodizing and coating directly alter final component dimensions. Oxide layer thickness and coating build-up vary with process parameter, and non-uniform distribution leads to irregular dimensional change. However, existing research largely studies process behavior and measurement separately. With limited structural decision support for tolerance composition, current ISO GPN and SMU systems also do not explicitly account for surface treatment effect at the early design stage. This gap motivates the need for an integrated decision support approach, which form the basis of this study. The research gap and how this study is positioned. First, existing studies typically address machining accuracy, surface treatment effect, measurement, and tolerancing as isolated topics with limited integration into early-stage tolerancing planning. As a result, engineering decisions in high-mix, low-volume environments rely heavily on individual expertise. Without a unified framework, linking surface treatment induced dimensional change to tolerance allocation and measurement planning. To address this gap, this study proposed a prompt-based design for manufacturability, or DFM, calculation framework that integrates surface treatment effect, machining allowance, tolerance logic, and inspection planning, enabling more consistent and standardized precision machining decisions. The research gap and position this study within existing literature. As shown in the matrix, prior study tend to focus on individual dimensions such as machine accuracy, surface treatment effect, tolerance system or measurement and quality control, but these aspects are largely addressed in isolation. Very few studies integrate surface treatment-induced dimensional change with tolerance logic, measurement planning, and decision support mechanism in a unified framework. In contrast, this study uniquely combined machining accuracy, surface treatment, dimensional effect, ISO-based tolerancing, measurement and quality control, and also the FM-oriented decision support into a single cross-process manufacturability framework. This integrated positioning directly addresses the identified research gap and support more consistent and reliable engineering decisions in high-mix, low-volume precision machining environments. Let's summarize the research methodology used in this study, which is structured into 6 main steps. First step, the study starts with baseline data collection. This includes identifying surface treatment type and supplier, measuring coating thickness and dimensional build-up, classifying press fit requirement from FN1 to FN4, and validating the measurement system using MSA. Next, the second step, a composition model is developed by analyzing the relationship between treatment type and dimensional change. Based on this composition logic is established for each press fit class and mockup formula is defined to recommend pre-treatment machining allowance. In third step, the composition logic is translated into a Python-based calculator. The calculator takes treatment type, coating thickness range, and press fit class as input and outputs. The recommended machining dimension before surface treatment. The fourth step involves verification and testing through pilot implementation on selected production parts. Predicted dimensional are compared with actual post-treatment result and functional fit acceptance is validated. The model is refined if deviations are observed. Once verification, we go for step number 5. The calculation logic is finalized and deployed. This includes freezing the model, preparing engineering guideline, and rolling out the calculator for engineering and MPI use. Finally, the sixth step, post-launch monitoring is conducted by tracking internal and external DPPM trend, rejection rate related to feed and tolerance issue, and quantifying cost of poor quality reduction for continuous improvement. In conclusion, I found that surface treatments such as anodizing and coating introduce dimensional change that significantly affect tolerance decision in high-mix, low-volume precision machining. Current tolerancing and measurement practice do not sufficiently capture this effect during early design stage. To address this, I propose a prompt-based design for manufacturability decision support approach that integrates surface treatment effect with machining allowance, tolerance logic, and inspection planning. This approach supports more consistent engineering decision, improve dimensional accuracy, and help reduce rework, scrap, and overall quality-related costs. If a clear understanding on how surface treatment introduces dimensional change in precision components, the study provides a structural logic to support early-stage tolerance planning rather than relying purely on individual experience. This leads to more consistent engineering decision-making, improved manufacturability, and better dimensional accuracy. Overall, the outcome from a practical foundation for developing future design for manufacturability decision support tools in precision machining environments. Here listed the 12 main references that I used for this study. These references are selected from recent and relevant studies covering surface treatment effect, tolerancing system, measurement, and quality control, and decision support in manufacturing which collectively support the theoretical foundation of this study. I would like to acknowledge Solid Bond Precision's manufacturing senior heart for providing technical support, industrial insight, and data that enable this study to be grounded in real manufacturing practice. Thank you for listening to my presentation. I welcome any question from the floor.